Hello everyone, I am Abhranil, a visiting faculty at National Institute of Science Education and Research, Bhubaneswar. This talk is based on my recent research work on identity testing and non-commutative rank computation over the free Skew field. This is joint work with V. Arvind, Utsab, Ghosal, Partha, Mukhopadhyay, and C. Ramya. So the plan of the talk is as follows. We'll first introduce the rational identity testing problem, the main focus of this work, and then we'll briefly mention our results of this work one by one. Okay, so let's start with some introduction to rational identity testing problem. Before we tell you what is rational identity testing problem, let us go over what is polynomial identity testing problem. Okay, so we are familiar with polynomial identities. It is everywhere in mathematics and theoretical computer science. And to check that these are indeed polynomial identities, we can just expand it monomial by monomial and check the coefficients are same or not. Or equivalently, we can like only one polynomial is given and we can check whether the coefficient for every monomial is 0 or not. But for multivariate polynomial, it can have exponentially many monomials. So it is important how the polynomial is represented to us. So arithmetic circuit is used as an efficient representation of multivariate polynomials. So if you are familiar with Boolean circuits, you can think of it as an algebraic analog of Boolean circuits, where the input nodes are labeled by variables or scalars from the underlying field, and the internal nodes and the one designated output node labeled by some basic arithmetic operations like addition or multiplication. And in that output node, you are computing the polynomial of your interest. And similar to the Boolean setting, if the fan out of each internal node is at most 1, then we call it an arithmetic formula. So just like arithmetic circuits and arithmetic formulas, the other computational model of our interest is algebraic branching program, which is again a directed acyclic graph, but this time the edges are labeled by some linear terms, some polynomial of form alpha 1x plus alpha 2x2, and there is a designated source node and a designated sink node. And if you look at any source to sink path, it computes the product of linear forms depending on the linear forms labeling those edges participating in that path. And the final polynomial being computed is like if you take the sum over all source to sink path, this product of linear forms, sum of product of this linear forms. As you can check in this example, this is the polynomial being computed. Okay. So now we can define the PIT, the polynomial identity testing problem formally, like given a polynomial given by an arithmetic circuit or formula or an ABP, we want to decide whether it is computing a zero polynomial or not. Okay. So the PID problem is of two types. The first one is like white box, where we can see how the circuit is computing the polynomial. That we can exploit the circuit structure. This is called white box algorithm. And the second one is black box PIT, where the polynomial is given to us as an evaluation oracle. And our goal is to find a non-zero evaluation. Here we are using the semantic meaning of a non-zero polynomial. If a polynomial is non-zero, then we know that there would exist a non-zero evaluation. A witness, you can think of it as the witness of its non-zeroness. We will be able to find a non-zero evaluation. And black box PIT asks to find such a witness. So as in the black box, we can't see the polynomial. So you can think of like the goal is to output a list of evaluations so that for every non-zero polynomial, in that list of evaluation, you'll be able to find a witness of its non-zeroness. Okay, so it's like a list that works for all the polynomials. So this list of evaluations is formally called a Hitting set. So a Hitting set H with respect to a circuit class C is defined as the list of evaluations so that for every non-zero polynomial in the circuit class C, by non-zero we meant that there is some witness in the universe, and we'll be able to find a witness in that small list of evaluations in that Hitting set. Okay. So for example, you can to get some intuition, you can take this simple example that when the circuit class is like the polynomials of all infinite polynomials of degree at most t, then a list of d plus 1 many points, it serves as a hitting set. It will be a hitting set. Okay, and inductively you can show that if instead of infinite polynomial, if you go to n-bit polynomial of degree d, you can construct a hitting set of size d plus 1 power n. Okay. Due to polynomial identity lemma, it is known that a commutative circuit, we can do PIT in randomized polynomial time, this black box PIT, and de-randomizing this black box PIT, commutative PIT, is an interesting open problem. So this is all about commutative PIT. Let us now move to non-commutative computation. So till now, whatever we discussed, we didn't distinguish between x1, x2, and x2, x1. These are considered as the monomers. But suppose now we are imposing some restriction on the multiplication heads. You're saying that, okay, the left child into right child and the right child into left child will distinguish between them. So x1, x2, and x2, x1 will consider them as two different non-commutative monomers, or as we'll consider them as string. Okay, and it computes non-commutative polynomial in the free algebra. So now we can define non-commutative PIT. So in this case also, for non-commutative computation also, we can define non-commutative circuit formula, non-commutative AVP. So given a non-commutative polynomial by some circuit AVP or formula, the goal is to decide whether it is computing a zero polynomial in the free algebra or not. So how different is it from the commutative setting? You can get some idea from this simple example, like x1, x2, x1 plus x2 into x1 minus x2 is equal to x1 square minus x2 square. It is a polynomial identity in commutative setting, but it is not an identity in the non-commutative setting, because that monomials x1, x2, and x2, x1, they're not going to cancel out each other. But now the black box PIT becomes quite tricky, as we have said that for every non-zero polynomial, there will be a witness of its non-zeroness. But like if you take the first one, that it is not an identity in the non-commutative setting, but whatever the value you substitute from the field, you will not be able to tell that it's not an identity. So now the idea is to go to matrix algebra. So here we define hitting set as like a list of matrix evaluations. Okay, so for every non-zero non-commutative polynomial, there is a matrix tuple, a matrix evaluation as a witness of its non-zeroness. Okay, and the goal is to find such a witness. So what is known due to Ford's and Spilka, it is known that if we have a non-commutative polynomial computed by a formula of polysize, then we can construct a hitting set of quasi-polynomial size. Okay. Okay, so now whatever we have discussed, we are using addition and multiplication as basic arithmetic operation. Now suppose we are using division or equivalently the inverse case. Okay. So even the commutative setting, we use an inverse gate. It computes, we use more than one inverse gate. It computes commutative rational functions, and it has a canonical representation, like any commutative rational function can be represented as a ratio of two commutative polynomials. So if you want to test whether a commutative rational function is zero or not, it essentially reduces to commutative PIT. But in the non-commutative setting, when you introduce inverses, then it becomes very complicated. Formally, it computes non-commutative rational function in the universal free skew field, which is quite well studied in mathematics for several years. So formally, what is this non-commutative rational function? So in this talk, we'll see different definitions of non-commutative rational function. Right now, let's start with the first definition given by Amisu, which says that consider all non-commutative rational expressions. Okay, and any two rational expressions, for every matrix substitution, whenever both of them are defined, it may happen that one of them is defined but the other one is not defined. We ignore those substitutions. Whenever both of them are defined, if they agree, then we say that these two expressions are computing the same rational function. Okay, So you can think of like, given this set of all non-commutative rational expressions, modulo this relation, those equivalence classes we call non-commutative rational function. Okay. And unlike commutative setting, here it doesn't have any canonical representation. Like, you can't express it as like ratio of two non-commutative polynomials, or you can't just expand it as like monomial by monomial. So it is quite different from the commutative setting. And here also, one important parameter is the inversion height, the number of nested inverses. If you look at a path from leaf to root, how many inverses are there? Okay, so in commutative setting, as we have seen that we can always express it as like ratio of two commutative polynomials. We can push the inverse gate at the top of the circuit, so we can as well think that there is only one inverse gate in our circular formula. But in case of non-commutative setting, the number of nested inverses, it's like how complicated our rational function is. It depends on the number of nested inverses it has. And it was shown by Rose and Wigderson that if we consider a sizes formula, we can bound this nested inverses, the inversion height, by order log s. Okay. So Rose and Wigderson also defined this rational identity testing problem, that given a non-commutative rational formula, we want to decide whether it is computing the zero function in the universal free script, or equivalently, that does there exist a matrix substitution of some dimension where if we evaluate the non-commutative rational formula, it is defined and it is non-zero. We want to find such a point. So how non-trivial it is, you can get some idea from this simple identity, which is known as was identity. We don't have any trivial algorithm to check that it is indeed a rational identity. So what is known about this problem? So due to Gard, Goodwitz, Oliver, and Wigderson, it was shown that in deterministic polynomial time, we can solve RIT in white box. Later, it was extended over finite fields also by Ivanov, Utsab, and Subramanian. In black box, for general rational formula, we have a randomized polynomial time algorithm due to Turkson and Markham. But we have a deterministic quasi-polynomial time algorithm only for rational formulas up to inversion height 2. Only the first level of nested inverses. Recently, in a joint work with Arvind and Mukhopadhyay, we showed that. But de-randomization of black box RIT for general rational formula is open. Okay. So this was the state of the art, and now let us start with our first result, the relation between non-commutative hardness and RIT de-randomization. So our goal is to de-randomize RIT, and what we thought that can we reduce this RIT de-randomization problem to proving lower bound to another problem, which is like probably easier to solve, like proving lower bound problem. So the intuition comes from the commutative setting, where due to the result of Covenants and Impagliazzo, it is known that if you can show the hardness of the permanent polynomial, it implies PIT de-randomization. Okay, so it is known that hardness implies de-randomization in commutative setting. What about non-commutative setting? It turns out that there is a similar result in non-commutative setting also due to Bogdanov and Wei, who showed that, I mean, they can point out any single polynomial, but if you consider any k-dimensional matrix algebra and consider the class of all polynomial identities of that k-dimensional matrix algebra, if the ABP complexity is exponential, is 2 power k for all the polynomial identities, then it implies de-randomization of non-commutative formula and non-commutative ABP. Okay, so it is quite reasonable now to guess that RIT will be able to de-randomize the RIT also using some hardness assumption. Now the interesting question would be to pinpoint what will be the assumption, or in other words, how much we need to strengthen. Do we need to strengthen the hardness assumption to get this RIT derandomization? Surprisingly, what we get that the same hardness assumption suffices to derandomize RIT also, almost for general rational formula. So more precisely, what we show that the same hardness assumption would give you a quasi-polynomial size heating set for rational formulas of constant inversion height. And for rational formula of sizes and inversion height log s by log s, we get a sub-exponential time algorithm. So just recall that a rational formula of sizes, the inversion height is bounded by order log s. So it captures almost the entire class of rational formulas. Okay, so let us just go over the proof idea of this result. So it has two main components. The first one is a variable reduction step. That given a rational formula, inverted rational formula, we come up with an encoding such that the first property is that the encoded rational formula is only over 2 into h plus 1 many variables. And second property is that it preserves identity. Okay, so this is the first step, that we reduce the number of variables, preserving the identity. And the second step is that we bound the dimension of the defined point. If the rational formula, given rational formula is of sizes and inversion at h, we show that it cannot be an identity for log s for h plus 1 dimensional matrix algebra. In other words, if you give me a rational formula R of sizes of inversion h, and if I substitute, there would exist a weakness from this dimension. Okay, to prove that, we use ideas from matrix coefficient realization theory, which essentially allows matrices to interleave between non-commutative variables also. In this general setting, it was extensively studied in this paper done by Volchich in matrix coefficient realization theory, and also in our recent work where we showed this quasi-polynomial size heating set for inversion at 2. Okay, now using these two components, what we can now do, given a rational formula, inverted rational formula of sizes and height h, we just we do PIT for the encoded rational formula, which is like 2 to h plus 1 variant, and where we have we know that it is defined on matrices of this dimension log s for h plus 1, and essentially boils down to commutative PIT, where we have the degrees like polynomially bounded and number of variables are logarithmically bounded for constant inversion height. That gives us the quasi-polynomial size heating set. Okay, so this is the first result that we have. Now let us move to invertibility of matrices over the field field, and let us first go over what is its relation with the RIT problem that we are discussing. So, as we have said, that the rational for the rational function can be defined in different ways. We have seen the definition given by Amisul. The second definition now we look at, given by Kohn, would define a non-commutative rational function that for every non-commutative rational function, there is a linear matrix, the entries are like alpha 1 x1 plus alpha 2 x2, each entry. And if you compute its inverse over the free skew field, okay, then that rational function is computed as one of the entry of the inverse of that linear matrix. Okay, so what Rubis and Gresham showed, they strengthened this definition by showing that if the rational function is computed by a rational formula of size s, then the corresponding linear pencil that you'd look at, the size of the linear pencil will be at most 2s. Also, like given a rational formula, suppose we want to do RIT for that rational formula, Now we'll look at the corresponding linear pencil of R inverse. Okay, it is known that if R is non-zero, if and only if R inverse is defined. Okay. Now what we will do that we'll check whether the corresponding linear pencil corresponding to R inverse, whether the linear pencil is invertible or not in the free skew field. Okay, that will tell us whether R is 0 or not in the free skew field. So this problem is known as singular problem, which you can think of like the non-commutative version of Edmonds problem, which is like an interesting open problem that captures the commutative ABP PIT. Okay. So what is known about this problem? For RIT, the results that we have mentioned, actually those results reduces RIT to singular problem and gives a deterministic polynomial time for singular given a linear matrix to check whether it is invertible or not in the free skew field. Now suppose we want to study singular in more general setting where we also allow some non-linear entries in the matrices, okay, some polynomial entries. Then what is known? So in the same paper, Gerd, Gulbis, Witters, and Oliveira, they showed that it admits the deterministic polynomial time algorithm even when the entries are computed by small non-commutative formula. Okay, so the main idea that they had, they reduced this case to deciding invertibility of a larger linear matrix. Okay, so now the question that we have is that can we generalize it further? They generalized it up to when the entries are computed by some non-commutative formula. Now suppose that entries are computed by non-commutative ABP or even non-commutative rational formula. What we show that this singular problem, it admits the deterministic polynomial time Markov algorithm even when the entries are computed by this non-commutative ABPs or non-commutative rational formulas. The main idea that we have is again a gadget construction that reduces to this linear case, but the construction that we have is quite different from the construction that was mentioned in the previous paper. The main idea here, what we use is that if the entries are computed, if it has a small linear pencil, then we can, it's kind of linear pencil composition idea. Then we can always construct a larger linear matrix such that the invertibility of that input matrix follows from the invertibility of the new linear matrix. Okay, so this is the second result that we have. Now let us move to our final result, characterization of linear pencil representation. So as we have mentioned that for every rational formula of size S, Rubis and Wigderson, they showed that there is a corresponding linear matrix of size 2S. What about the converse? That is it true that for every linear matrix, if you look at the inverse of it, each entry will have a small rational formula? Is it true? Rubis and Wigderson showed that it is not true. Indeed, if you have a symbolic matrix, you look at the inverse of it, for an entry, it needs like exponential size non-commutative formula. There is an exponential separation. But if we allow rational circuit instead of rational formula, then each entry of the inverse can be computed by polysize rational circuit. So if you consider these classes, RF for rational formula, LR for or all those rational functions that have small linear representation, and RC, those rational functions that have small rational circuit. So the first one is a proper containment, and second one, we know that this linear representation, this class is contained inside RC. Now the question we would like to ask, can we identify a circuit class that would exactly characterize the linear representation? So if you are familiar with the computer setting, you can think of like that it is exactly similar to the determinant representation. We knew that determinant representation sits inside formula and circuit, and we came up with this ABP model that exactly characterizes the determinant representation. In non-commutative case, can we come up with some circuit class that exactly characterizes this linear representation? Okay. So to do that, first of all, we can't solve this problem. We are not able to solve this problem, but we make a partial progress in solving this problem. So what we do, before we state, we define a new model, but before telling you that new model, let us go for a third definition of non-commutative rational function. So it was defined by Bergman, who defined a non-commutative rational function of height h. Suppose you have a polynomial expression where some of the variables you are replacing by non-commutative rational function of inversion at h minus 1. This is the way to construct a non-commutative rational function of height h. This definition was given by Bergman. And the new model that we defined, which we call inversely disjoint rational R-square circuit, where this polynomial expression that we have, it is computed by a non-commutative R-square circuit, or equivalently by a non-commutative ABP. Okay, and whenever we are like composing we are replacing this variable by some inductively built circuits of height h minus 1, this will be inversely disjoint. Those G1 inverse and G2 inverse, they will be pairwise disjoint. But we show that this class, this inversely disjoint rational R-square circuit, it has a small linear pencil. Okay, so that puts it inside, in between the class of rational formula and linear representation. Moreover, if we remove this inversely disjoint restriction, then the class sits in between linear representation and rational circuit. In this containment, we know that out of the first two containments, one must be proper, but we don't know which one is proper. Okay, so yeah, that's all. Thanks for attending.